All right, this is the second video on partial fractions. Before working this video or before watching this video, you should make sure you're very comfortable with the process of partial fractions that we went through in the first video. And you should have completed the first 3 problems on the worksheet and made sure you're able to get those answers correct. I want to quickly go through this example. This is similar to what was on the previous video. So this ends up being partial fractions, and we factor the denominator. So we come down to the bottom here and factor x squared minus 4 into x plus 2, x minus 2. Again, from before, we talked about partial fractions being the process of trying to find smaller component fractions that result in this this fraction 4 over x plus 2, x minus 2. So what we did in the last video is we said, okay, it's going to be a over x plus 2 plus b over x minus 2. We multiply by the common denominator, which is x plus 2, x minus 2, and we think of that as being over 1. On the left-hand side, that cancels the entire denominator, and we get 4. On the right-hand side, on the first fraction, the x plus 2 cancels. On the second fraction, the x minus 2 cancels. So now you distribute a, you distribute b, and you combine like terms. So you get a plus b times x plus negative 2a plus 2b. Now, the polynomial on the left is 4. The polynomial on the right must also be 4. Because there's no x on the left, that means that there really can't be an x on the right. That means the coefficient of x needs to be 0, so a plus b is 0. Negative 2a plus 2b has to be 4 for these two things to be equal. We solve that for a or b however we want. I'm going to multiply the top by 2 so that I can get the a's to cancel out. So if I now add these, I get that 4b is equal to 4, which means b is 1. A plus b is 0, so a plus 1 is 0, which means a is negative 1. So I use that process to come back up to the top and rewrite this as negative 1 over x plus 2 plus b over x minus 2, so 1 over x minus 2 dx. We split that into 2 integrals. Both of these are quick u substitutions where u is the denominator, du is 1 dx. So we get negative natural log absolute value of x plus 2 plus natural log absolute value of x minus 2 plus c, and that's the answer. On this video, I want to look at more cases as to what can happen in the denominator. Here, we call these linear factors. Linear means means a polynomial of degree 1, which means the highest power of x is 1. In general, we're going to deal with partial fractions decompositions where we end up with linear factors and what's called irreducible quadratic factors. We will not deal with irreducible polynomials of higher degree than 2. When we have a cubic, a third degree, if we think about the graph of a cubic, there's always an x-intercept, which means that cubics always factor more. There are 4th degree polynomials that won't factor. We won't deal with those, but we will deal with stuff that will factor down into linear factors or irreducible quadratic factors. Irreducible quadratic means 2nd degree x squared, but does not factor at all, even if we allow for square roots. The key way to check for that is that the discriminant in the quadratic formula, b squared minus 4ac, is less than 0. If that's the case, that's an irreducible quadratic factor. When we deal with these, you can have what's called distinct linear factors and distinct irreducible quadratic factors, or you can have repeated linear factors or repeated irreducible quadratic factors. There are two things that are important about these. Two things that we're going to talk about these. One thing is it's important how you handle the partial fractions decomposition. So up here we have linear factors. They're distinct because they're not the same as each other. When we have that, the partial fractions decomposition, so we're going to abbreviate that here as PF, the partial fractions form is going to be like A over the first thing. So let's say that one of the distinct linear factors is like 3x plus 4, and another one is x minus 7. Then you put a constant over top. The idea on these is that the degree of the numerator needs to be strictly less than the degree of the denominator. The degree of the denominator in both cases there is 1. The degree of the numerator then is 0. The degree is the highest power of x. So degree 0 means just a constant. Degree 1 means linear. So when we do the partial fractions decomposition, meaning when we set up this form like we did in the last problem, you put a constant over top of each of the linear factors. If you have a repeated linear factor, that's like if I have 2x plus 5 to the third power, or if I have x minus 3 to the second power, or if I have x to the fifth power. So if x is there to the fifth power, that's considered repeated linear. The partial fractions decomposition for those things looks like this. So the power itself gets its own fraction, and every power underneath it gets its own fraction. So when I have 2x plus 5 to the third, I use a over 2x plus 5, b over 2x plus 5 squared, c over 2x plus 5 to the third. When I have x minus 3 squared, I have d over x minus 3 and e over x minus 3 squared. And now I'm going to cheat because I don't want to write out 5 terms for x to the fifth. Let's say that is x to the third. Then I have f over x, g over x squared, and h over x to the third. So that's how we handle repeated linear factors. The rationale for that is that all of the lower powers, if we were to get a common denominator, could contribute to a common denominator of the higher power. So if you look at the last three fractions there, the common denominator for x, x squared, and x cubed is x cubed. The common denominator, and I made a mistake, this is x squared, or x minus 3 squared. The common denominator for x minus 3 and x minus 3 squared is x minus 3 squared, and so on. Okay, so that's how we handle it when we do the partial fractions decomposition. The other important part is how we handle the integrals. So when we do the integrals, how do we evaluate those? Well, on the last video and so far on this video, we've gotten integrals where the denominators are distinct linear factors. On those problems, those are log forms. So we use the log form when we do those. When we have higher powers and they're repeated, so if I have 2x plus 5 squared or 2x plus 5 to the third or x minus 3 squared, those are power functions. So you bring those up and make it like b times 2x plus 5 to the negative 2. So when we do integrals, we use log forms for some and power functions for the other. So we use log rule for the ones that are the first power. We use the power rules for the ones that are the higher powers. We'll talk about irreducible quadratics a little bit later. I want to work through another example. So if we look at this, I've already factored the denominator for us, but it factors into a linear factor x and a repeated linear factor 4x plus 3 squared. So we have that there twice. We're going to use partial fractions decomposition on this. So we're going to come down to the bottom and we're going to rewrite this as 8x squared plus 19x plus 9 over the bottom is x times 4x plus 3 squared. And now we want to write out the partial fractions decomposition. So the form of that is that we want a over x and then b over 4x plus 3 and c over 4x plus 3 squared. So again, when you have a repeated linear factor, let's say it was to the 4th power, then you would get a fraction for the 1st, 2nd, 3rd, and 4th power when you're writing the expansion. We're now going to solve this for a, b, and c. So we're going to multiply by the common denominator. And it's real important that we think of it as multiplying by the common denominator over 1 rather than some type of cross multiplication. So if we do this on the left, the entire denominator cancels. That means we get 8x squared plus 19x plus 9. On the right-hand side, on the first fraction, the x cancels, so we get a times 4x plus 3 squared. On the second fraction, one factor of 4x plus 3 cancels, so we get b, we get x, and we get a single factor of 4x plus 3. And on the third fraction, the 4x plus 3 squared cancels, so we get cx. Now there's a little more algebra to do, but the goal again is to solve for a, b, and c. So we're going to multiply this out and get 16x squared plus 24x plus 9. We're going to distribute the bx, and so we get 4b, I don't know why I'm putting equals there, that should be plus, but we should get 4bx squared plus 3bx, and then cx, and we get on the left 8x squared plus 19x plus 9. We distribute the a, we get 16ax squared plus 24ax plus 9a plus 4bx squared plus 3bx plus cx. And now we have some more stuff to combine. I'm going to scroll down a little bit, but we're going to get on the right-hand side, we're going to combine all the x squareds. That gets us 16a plus 4b x squared. It gets us for the x 24a plus 3b plus c x, and the only constant term is 9a. Now we equate the coefficients. So 16a plus 4b has to equal 8. 24a plus 3b plus c has to equal 19. And 9a has to equal 9. That means that a is 1. I can plug that into the first equation and get 16 times 1 plus 4b equals 8. If I subtract 16, I get negative 8 on the right-hand side, and divide by 4, I get negative 2 for b. And now I can plug both of those into the middle equation and get 24 times 1 plus 3 times negative 2 plus c equals 19. And now 24 minus 6 plus c equals 19. That gets me 18 plus c equals 19, which means c is 1. So we've got, I'm going to write it up here just so we'll be able to see it. We've got a is 1, b is negative 2, and c is 1. We go back up and rewrite this as the integral of 1 over x plus b, so negative 2 over 4x plus 3, plus c, so 1 over 4x plus 3 squared, dx. Now we have more to do on this problem, but this work is to get that decomposition. If we go back up and look at what I've written up here, the partial fractions decomposition part, what I mean is how I did this decomposition to begin with. I used a linear one for x, so it's a distinct linear factor. And then for 4x plus 3 squared, it's a repeated linear factor. So each power got its own fraction, everything from 2 down to 1. Now, when I talk back up here about the integrals, I'm talking about how do we handle these integrals now? Well, these are log and power rules. So if I split this up, I get 1 over x. That's the basic form for log. On the second problem, I get -2 times the integral 1 over 4x plus 3. And on the third problem, I'm going to want to write that as 4x plus 3 to the -2 dx. On the second two problems, we're going to do a quick u substitution where u is 4x plus 3, so du is 4 dx. Now, the integral of the first one is log absolute value of x. On the second one, we would do the u substitution. I'm not going to show all the steps of that, but you can if you would like to do that. We're going to get a 1/4 outside and then log absolute value of 4x plus 3. And then on this one, we're going to get 1/4, but then it would be u to the -2 du. So we get 1 over -1 u to the -1 plus c. And now we plug back in and simplify. So we get natural log of the absolute value of x minus 1/2 natural log absolute value 4x plus 3 minus 1 over 4 times 4x plus 3 plus c. That's the answer on this problem. Okay, so that's how we handle when we have distinct linear factors. That's how the first problem was, that's how part of this problem was, and that's how all of the videos on the, or all of the problems on the previous video were. When we have repeated linear factors, this is how we deal with them. If we had a higher power than 4x plus 3 squared on the bottom, if it was to the third, we'd bring it up and make it -3, and so on. On the partial fractions, this is how the algebra works. It might be a little bit more tedious, especially when there are 3 or more variables to solve for. But basically, we're doing the same thing. And then the way we're handling the integrals are slightly different because of the forms. Now, that's for linear factors. When we have irreducible quadratic factors, quadratic means that you have degree 2. That's going to happen when we have something like this. So if I have like x squared plus 9, we'll make that 16x squared plus 9. X squared plus 9 would also be a distinct linear factor. So if I had, or I'm sorry, distinct quadratic factor. But if I had 16x squared plus 9, or if I had x squared plus 2x plus 5. Okay, so on the partial fractions decomposition, then what we do is each one gets its own fraction, but because it doesn't factor at all, the denominator has degree 2. Well, the idea is that the numerator would be a smaller degree, which means we don't know whether it's degree 1 or degree 0. So what we do is we kind of assume that it's degree 1, but we allow for the possibility that a might be 0. And if that's the case, then the degree of the numerator would be degree 0. But we put ax plus b. Same thing when we have x squared plus 2x plus 5. Then we put something like cx plus d in the numerator. Just keep the numerator's degree smaller than the degree of the denominator. When we do the integrals, we actually covered this type of integral, this first one with no middle term, on a video when we talked about u substitution. You end up using log and inverse tangent. So you use log and inverse tangent if you have an a and a b. So if a and b are both non-zero, then you'll use log and inverse tangent. If it's just b, if a is 0, you use only inverse tangent. If b is 0 and a is something else, then you use only log. You actually use log and inverse tangent on the second type of problem, but we'll talk more about that in the next video. Okay, and then repeated irreducible quadratics, that would be if we had something like x squared plus 9 to the third, or x squared plus x plus 1 to the second. Again, we can verify that those are irreducible quadratics by calculating the discriminant and proving that that's 0. But in this case, we handle it like we handled repeated linear factors. So x squared plus 9 to the third would get 3 fractions in the decomposition. We'd have x squared plus 9, we'd have x squared plus 9 squared, and we'd have x squared plus 9 to the third. In all 3 of those, the degree of the numerator we would assume to be degree 1, but allow for the possibility of degree 0 because the coefficients of x might end up being 0. So we would put something like ax plus b, cx plus d, or ex plus f. For x squared plus x plus 1, that's also irreducible. When it's squared, we use the first power of the quadratic and the second power of the quadratic, and then we'll put gx plus h and ix plus j when we do those. The integrals of these are not going to be covered extensively in these videos, so we won't cover them, but typically we'll use something called, we'll use trig substitution to solve most of those. So we use log and arctangent for the first power, and you use trig sub for the second power. So log, arctangent, and trigonometric substitution. Those are complicated integrals that we probably won't spend a whole lot of time on. Okay, so this is a summary of, first of all, how to break it down when you're trying to use partial fractions, and then how to do the integral once we've got the decomposition. The next thing I want to talk about is how do we know when we use partial fractions composite or partial fractions decomposition. So to use partial fractions, you need 2 things to be true. First, you need a proper rational expression. A rational expression is when you have a polynomial over a polynomial. Proper means the degree of the numerator is less than the degree of the denominator. And so informally, we'll say the degree of the top is less than the degree of the bottom. We also need the bottom to be factorable. So it needs to break down some. We talked a little bit earlier about the fact that all cubics, so all third degree polynomials, will factor some. Fourth degrees don't necessarily have to, but for partial fractions to work, we need to be able to factor the denominator. Okay, so we're actually going to do 2 more videos on partial fractions. The next video we'll do a couple more examples and show what happens if the degree of the top is not smaller than the degree of the bottom. In the last video, the 4th video, we'll talk about how to handle irreducible quadratics in the denominator if the middle term is not 0. For now, you should practice some more problems before the next video. On the 8 problem worksheet, the first partial fractions worksheet, problem 4 has an irreducible quadratic in the denominator. You should skip that problem for now, but it would be a good idea to do the rest of the problems. So it would be a good idea to do problems 5 through 8 before the next video. So to go ahead and work on 5 through 8. The next video we'll talk, or the next 2 videos we'll get prepared to do the rest of the problems. All right, thanks for watching.